Properties of logarithms. So chapter 5, section 5. So let's get into the properties of logarithms. We already looked at the properties of exponents, and we can kind of surmise some of these properties because we know that the logarithm function is actually the inverse of the exponential function. So we should see things that kind of blend in with it. So log base a of 1 is equal to 0. Remember, that's the equivalent of saying a to the 0 is equal to 1. Log base a of a is equal to 1. That's the same as saying a to the 1 is equal to a. A to the log base a of m is equal to m. Well, that's just using the fact that they're inverses of one another. Whatever you do with the exponential function can be undone with the logarithmic function, or in this case, whatever you did with the logarithmic function is being undone by whatever you do with the exponential function. So the reverse of that, log base a of a to the r is equal to r, where m and a are the positive real numbers, a is not equal to 1, and r is any real number. Well, let's get some more properties of logarithms. The log of a product and the log of a quotient. If you have log base a of a product, m times n, that can be broken up into two separate logarithmic expressions, log base a of m plus log base a of n. Well, if you're thinking about that, we're talking about the inverse of exponentials. Remember that a to the m times a to the n is equal to a to the m plus n. So log base a of m times n is equal to log base a of m plus log base a of n. If we have a division, log base a of m over n, then log base a of m minus log base a of n is equivalent to that. Again, think of your exponential rules, and this follows along. The log of a power equals the product of the power and the log. So log base a of m to the r is equal to r times the log base a of m. So if you have an exponent in your logarithm, log base a of m to the r, then that exponent can be pulled out front as a multiplier or a coefficient. And then a to the r is equal to e to the r times the natural log of a. So a number of properties. So let's use some of these properties, rewriting logarithms. So I want to rewrite log base r of 6 to the 5th n to squared over t to the 7th as an expression created by adding and subtracting logs without exponents. So basically, we're going to put to use these things that we just saw here, that if we have a product inside of our log, that can be written as two separate logs that are added together. If we have a quotient inside of our log, that can be written as the difference of two logs. And if we have an exponent inside the log, we can pull that out as a multiplier. So let's see what we got here. So we got log base r of g to the 5th n squared over t to the 7th. And we want to put that as an expression of adding and subtracting logs without exponents. So first thing we can do is we know that quotient we can separate out. We have log base r of g to the 5th n squared over or divided by t to the 7th. So we can break that into two pieces, log base r of g to the 5th n squared minus log base r of t to the 7th. Now that we've done that, we can break apart the product. We have log base r g to the fifth times n squared. We can break that product apart as an addition, log base r of g to the fifth plus log base r of n squared minus log base r of t to the seventh. Now that we have that, we can take our exponents and just take them out front. So 5 log base r of g plus 2 log base r of n minus 7 log base r of t. So the process, we separated out the division by making it a subtraction of logs. We then separated out the product by making an addition of logs. And then we brought out the exponents by making them coefficients or multipliers. Well, what about the other direction? What if I want to rewrite 4 log base 8p of p minus 5 log base 8 of y minus 2 log base 8 of m minus 6 log base 8 of t plus log base 8 of x as a single logarithmic expression without coefficients? So I want to combine this all together into products and quotients, and I want to take those coefficients and turn them back into exponents. So the first thing I'm going to do is I'm going to get rid of those coefficients. I'm going to make them exponents. So 4 log base 8 of p becomes log base 8 of p to the fourth. 5 log base 8 of y becomes log base a of y to the fifth. 2 log base 8 of m becomes log base 8 m squared. 6 log base 8t becomes log base 8 t to the sixth. And log base 8 of x becomes log base 8 of x. That doesn't change. Now what I'm going to do is, just for simplicity's sake, and you don't have to do this. When you get better at this, you'll recognize that you can just do this without doing this step. I'm just going to pull together the pluses. I've got plus log base 8 p to the fourth, and I've got plus log base 8 of x. So I'm just going to bring those together, giving me log base 8 of p to the fourth plus log base 8 of x. Then all my subtractions, minus log base 8 of y to the fifth, minus log base 8 of m squared, minus log base 8 of t to the sixth. Now we could pull out that common factor of minus 1 in those last three and make that minus and have my product there. But I'm just going to take it to the next step, where I'm going to look and say, well, now I've got the pluses, they're going to be on the top. I've got the minuses, they're going to be on the bottom. So log base 8 of p to the fourth x over y to the fifth m squared t to the sixth. And this is where I said, when you get better at this, you'll recognize, oh, if there's a plus, if it's a positive or a plus, then it's going to go in the numerator. If there's a subtraction, it's going to go in the denominator. So I could have just read that off of the previous equation and said log base 8 p to the fourth, that's in the numerator. Log base 8 y to the fifth, that's in the denominator. Log base 8 m squared, that's in the denominator, minus log base 8 t to the sixth, also in the denominator, plus log base 8 of x in the numerator. And I could just pull the pieces together. And I gave you a little more complicated one so you can see the different pieces of it, as opposed to running through a lot of the simpler ones. Well, let's talk about the change of base formula. As I said, some calculators have the ability to take the log of a base other than e or 10. If your calculator does not have that, then this is where you need to be. If you have a TI 83, chances are it doesn't have that capability. If you have a TI 84, depending on the firmware that you have on it, it may or may not have this capability. An 83 will not. An 84 may. If it doesn't, you can download the proper firmware and load it onto the calculator, and then you'll be able to have this capability. It'll come into the equation, the library, or mathematical library. If you do not, if you have a standard calculator now, of course, for this class, you should have a graphing calculator. But that just because you have a graphing calculator, as I said, does not mean that you're necessarily going to have this capability. I believe that the Casio graphing calculators too, but my calculator, an old school calculator that I've had for longer than, wow, a lot longer than most of you have been alive, does not have this base capability. But what's cool is there's the change of base formula. And I used this to teach my daughter how to do it when she was using a TI-83 at home. And at school, they had the TI-84s, which had it built in. She had still had to do the work. So if A is not equal to 1 and B is not equal to 1, and M are positive real numbers, then the log base A of M is equal to log base B of M over log base B of A. So basically what it's saying is that if you have a log with a certain base of some value, that you can find that log by using a common base and just taking the log of that value over the log of the base, the original base. So B can be any common base. Well, what would we generally want to use? E or 10, right? If we can use base 10, then we can do it in our calculator. If we can use base E, then we can do it in our calculator. And with most calculators, this can be done very easily. So if you have a scientific calculator, you can just plug this in. So log base A of M is equal to the common log of M over the common log of A. Or it's equal to the natural log of M over the natural log of A, which may seem a little odd, but you can choose any base you want. We could change it to the log base 476 as long as we use that for both of them. Why you'd want to do that, I have no idea, but it could be done. So let's look at the change of base formula. Approximate log base 6 of 19 using natural logs. Okay, so log base 6 of 19, well, that's not a common log. That's not our natural log. This says use natural logs. So log base 6 of 19 is equal to natural log of 19 over the natural log of 6. If I plug log of 19 into my calculator, I get about 2.9444. If I plug in the natural log of 6 in my calculator, I get approximately 1.7918, which gives me when I divide that, I get 1.6433. So I come up with the log base 6 of 19 is equal to approximately 1.6433. Let's approximate it using common logs. Well, then I have log base 6 of 19 is equal to the common log of 19 over the common log of 6, which is approximately 1.2788 over 0.7782, which again gives me approximately 1.6433. Log base 6 of 19 is approximately 1.6433. So as you can see, and you can plug this into your calculator and verify that I'm not just giving you a snow job here, I'm not just making things up, but it does work. As long as it's got the same base in the numerator and the denominator, then it will come out with the same thing, even though using different bases will give you different values for the numerator and denominator. The ratio will always be the same.